Well, it is 1 o'clock Eastern, and we will get things started. Once again, hello and welcome to the October 4th edition of the Insights and Innovations webinar series hosted by the International District Energy Association. My name is Scott Seitzer, and I serve as the Director of Business Development for the association. Today's webinar is titled Special Pre-Operational and Post-Operational Actions Needed for New Large Closed-Loop Systems, presented by ChemAqua and PurgeRite. Before we kick off the presentation, I'd like to go over a few housekeeping notes. This webinar is scheduled for 1 hour, including the presentation, and approximately 15 minutes for Q&A, but we can run as late as 2:15 Eastern Time if we get enough questions. This webinar will be recorded and streamed on the IDEA website within 24 hours of its conclusion. Registrants will also be sent a follow-up email with links to the recording and the presentation slides. A link to the presentation slides is also provided in the chat box if you want to print out and follow along. Please submit your questions via the Q&A box during the presentation portion of the webinar. The Q&A icon can be found in the menu bar at the bottom of your screen. Questions will be reviewed by IDEA and posed to the presenters by the host at the conclusion of this presentation. Finally, if you're having any audio or video issues, please send a note in the chat function to IDEA's host, Jason Beal. Today's webinar will be of great interest for anyone involving the design, construction, commissioning, and operation of a large closed-loop chilled hot water system. Specifically, we'll discuss the need for flushing, including what velocities are necessary, the required testing and monitoring activities for these hot water systems, the best practice timelines to follow, and what types of disruptions might necessitate a remedial flushing, cleaning, passivation, and disinfection regimen, and what to do if you have to lay up your system or otherwise delay bringing your system online for an extended period after the flushing and cleaning and passivation process. You'll leave this webinar with a better understanding of the importance of proper flushing, cleaning, disinfection, and passivation of your hot water system, and how your organization can save money by preventing common problems, as well as what steps to take if you're experiencing any problems with your system. To discuss these topics, we're pleased to be joined today by several good friends of IDEA. Russell Buras is the CEO of PurgeRite. He's been a member of the PurgeRite team since the company's inception. He's worked the last 15 years in geothermal installation with a focus on developing and operating the mechanical flushing and purging business over the last 7 years. We're also joined by Jonathan Collins, who is a business development and estimator for PurgeRite. He has spent 7 years working in the oil and gas industry with an emphasis on design and manufacturing, and is currently focused on bringing awareness to the HVAC industry's need for proper hydronic flushing practices. We're also joined by Paul Liocci, a commercial and institutional corporate account manager for ChemAqua. For the past 14 years, Paul has worked within the industrial water sector with a primary focus on higher education and sustainability. He was a co-contributor to a cover story in IDEA's quarterly magazine in the winter of 2021 titled Florida System Conserves Water Resources with Reclamation. Without further ado, we're going to turn things over to our presenters. We'll start with a few comments from Pat Guccione, Vice President of Special Projects at ChemAqua. Pat, the floor is yours.
Great. Thanks very much, Steve or Scott. Again, welcome to everybody. And the reason we chose this topic, many of you know I've been working in the industry for over 45 years. And in my career, the biggest problems that I've seen in closed loop systems 95% of the time started because the systems were rushed and brought online without proper cleaning, flushing, passivation, and in some cases disinfection. So in order to help you avoid the pitfalls of that bad practice, we're going to go over what the good practice is. And with that, I'm going to turn it over to Paul, who's going to do the bulk of the presentation for ChemAqua today.
Yeah, good afternoon, everyone. Thanks so much for having us on and joining. I just want to do a quick little background about ChemAqua. So ChemAqua, we're a global company. We specialize in providing, water treatment services and solutions, on our corporate level, that we're based there. And I'm sorry, I lost my train of thought on that one. But yeah, our corporate headquarters is based in Dallas, Texas. And, yeah, we just kind of, really focus in this field, in this marketplace. And we're an industry leader when it comes to, higher education, district energy, and really look forward to maybe bringing some insight to these large, thermal storage systems and trying to fix you guys up on that.
All right, my name is Jonathan. I'm with PurgeRite, as Scott said. Thank you everyone for joining us today. It's a pleasure to be here to talk about hydronic flushing and preparing your hydronic system for commissioning. Real quick background about PurgeRite, some credibility about why we talk about this topic. So PurgeRite, we've been around since 2008. What we say is we're the mechanical flushing experts. We pride ourselves on our ability to clean and passivate a system so that the clients can achieve that designed efficiency that the engineers are going for. There's a lot of value in doing that, not only efficiency, but reduced maintenance costs and so many other things, which we'll get into later in the PowerPoint. Some of the primary sectors that we are asked to work in is mission critical, data centers, medical. All those medical campuses have large commercial HVAC systems, educational campuses, and then of course industrial and large commercial buildings as well. We get asked to work for a lot of large corporations. As such, we have flushed 7 out of the top 25 largest companies in the world, and that's by market cap. Any size system really is we're outfit for. There's nothing that's been too big for us to handle so far, and we intend to keep it that way. Like I said, our goal at PurgeRite is to thoroughly flush and purge your hydronic piping of any debris and air so that the system is fully cleaned and operates at designed efficiency. We do this all over the United States. Our temporary equipment, pumps and filters, we send anywhere in the United States. And our goal is to provide peace of mind to the client, to the general contractor, to the mechanical contractor, and the chemical companies in charge of these systems, that we're leaving it fully ready to be commissioned without any concern about contamination. So I'm sure everyone has seen a typical schematic, but these are the systems that we're going to be focused on when we talk about hydronic flushing. The two primary closed loop systems are going to be the chill water system and heating water system. Open loop, the open loop system, which is the condenser water, sometimes it's closed loop, that can be flushed from time to time, but primarily we're going to be addressing the chill water and heating water systems. And that said, go ahead and pass this off to Russell.
Thank you, Jonathan. Great job. So it's a pleasure to be with everyone today, and we're excited to talk a little bit about what will hopefully save you some headaches and some hassles and some problems down the road. Really, we got into this business and became a kind of a specialty service company, assisting mainly mechanical companies that have been tasked with doing this kind of work in the previous decades, because there really wasn't someone to kind of take it on. So we started digging into that and had learned a lot in the geothermal industry and brought that into the chilled water, heating water systems. And you can see even with some of these pictures, some of the reasons it's so critically important. These are all real pictures from the field. You cannot, people want to put in these systems, install these systems in a sterile environment, or they want them to be really clean. It just doesn't happen. I've been out in the field from a construction standpoint some years ago, and it's extremely difficult. We've recently been on a couple scenarios where the underground piping gets flooded while it's being installed. So all these systems really need to be, thought through to get them cleaned, because it's going to cause some issues. And you can see some of the issues if you have this in your systems. I've seen strainers not only clogged, I've seen, $500,000 problems, lawsuits over compressed strainers because the system wasn't flushed. You've got other maintenance issues and additional chemical costs, bio-growth, things like that. We'll talk about that. We did just recently have the pleasure of working with Princeton and flushing some of their systems on their new build that they're doing over the next several years. And there's already been noted savings on the systems that they're operating with the new pipe. And I mean, it's saving tremendous amounts of horsepower, of energy, and they're very excited about that. And I will put a plug in. I think Ted will be doing a presentation in San Francisco, maybe in more detail on that. And then we will also be doing a presentation that will have a lot more detail on that case study. So feel free to join us there. So some of the things that you need to really think about, you put in a new chilled water system, heating water system, and even geothermal. We didn't have it back on the slide. There's some things that really need to be thought of before you have things flushed. And I talked to a lot of engineers. We probably have some listening in today. The mechanical engineers design systems to operate. That's what they're paid to do, and that's what the design work, it revolves around. But the flip side of that is sometimes thought doesn't go into both the specifications and into the design of how we're going to clean this thing initially. Operational velocities and things like that are not necessarily the same as flushing velocities and what it takes to clean these systems. But before you get into actually digging into more of the flushing piece of it, some things you need to think of as an owner, as an engineer, chemical treatment company, if you're involved in the project team like ChemAqua, or if you're involved in some other way of kind of planning, the general contractor or mechanical. These are some things you need to check off your list. One is we are considered a third-party flushing company, so we're bringing in external equipment, as you saw in some of those previous slides, external pumps and filtration, et cetera. And we hook that up to not use the house pumps or not use the systems that are in place for the client, and to reach the velocities and to clean these systems. And before we show up, the piping needs to be hydrostatically tested and passed. And then a big issue these days is you need to have adequate makeup water, and power needs to be available. You really, one of the challenges we're seeing people wrestle with is, do they have enough makeup water? And I'm not talking 100 gallons a minute. I'm talking 500, maybe 1,000 gallons a minute capability to really take on the procedures that you need to do to flush. But then also, are you ready to turn your house pumps on, et cetera, when you're done flushing and the system has the proper chemistry in it to get that thing going? So this is an issue. Sometimes the power's not readily available, or it's delayed, and these enter into complexities of the projects. You want to be in compliance with the specifications. What that can mean is, as you look at some of the technical parameters in your specifications, typically found in Division 23 specs, there'll be certain flow rates that they're desiring to have done. In the chemistry part, there'll be certain durations that they want the chemicals circulated with. And so you want to make sure you're able to comply with that. And one of the issues there is that these systems can require other things, bypasses and such, and we'll talk more about that. And then also another thing that enter into some issues is, can your local municipality take on the discharge with the chemistry? In most places, I see it 90 in the high 90s. It's non-issue. The client or the general contractor should have a permit to do that. However, there are situations where they can't process it, so that becomes an issue. And that, of course, enters into your water disposal plan. So if you can't discharge, there are alternatives to that. We've deployed some of those, and you may have to look at that as an option. The other things you need to check out is to make sure that the water treatment providers reviewed the procedures with the mechanical contractors. Again, that would be on ChemAqua's to-do list, and we just did that project at Princeton with that team. And that the chemicals are on site, you got all your SDSs and everything ready to go. And then, as I've already stated, that you really have the system prepared to flush correctly. And again, that could require some extra bypasses, some valves, some procedure things you need to do to zone off the system. And again, those are not typically seen in your base design for building or constructing a new chilled water system. In order to complete these high velocity flushes, these are some of the components that we use deploy to just give everybody kind of a visual. So we bring in external pumps. So if you're doing a 24-inch chilled water line, let's call it carbon steel or something along those lines, or a heating water line, what we put together in our systems, and if we didn't do it, what a mechanical would try to rent or cobble together the equipment to do it, but it's kind of difficult, is first of all, pumps that are capable of moving the high velocity and high volume of water that you need. The picture there on the left is about a 5,000 GPM diesel pump. The blue one's just attenuated. It's the same thing, but it's attenuated. These are diesel-driven pumps. There are electric pumps, as seen in the picture. And then there's a variety of filtration vessels. And what we do and have seen be highly successful is you want to mate your pump with the proper filter vessel that can handle the flow. So if you're doing 5,000 gallons a minute, and we've done up to 60,000 gallons a minute, we're able to aggregate these components in whatever configuration we need to do, as Jonathan said, a very small system, or you can scale up to do a very large 42-inch pipe or whatever you need to do to meet the situation. One thing that we have tried to show people, and this hopefully will help everyone, and then we'll get into some detail, and then the ChemAqua guys will be able to chime in some more, is that this is kind of a flush process, just to kind of give a visualize that being a piece of pipe up above. And this is just recently installed, and say you're hydrostatically tested, you're good to go, and you show up and you typically have dirty water and you have debris in that. And really what we kind of have broken it down into several different phases, and there's some optional things that we'll get into a little more depth here as we go through the presentation. But there's really kind of, at a high level, it's 3 phases to kind of think about. And the first one is a clear water flush phase. And really the goal here is to move water and the volume of water to remove debris. And we have seen, as you saw in those pictures, glass bottles, cell phones, tools, wood, tubifores, just a myriad of things that get left in these systems that needs to be moved out of the way. They can get hung in valves later and cause all kinds of problems. So you want to circulate at a high velocity until the water is clear. And we also do a couple of things there. We'll bring in the full flow filtration the entire time, and we'll bring in makeup water and discharge simultaneously to circulating around the system. And so initially we'll kind of get that component going, and that's really kind of the first phase of this. Jonathan, go ahead and go to the next slide if you don't mind. Thank you. So that's the one I'm talking about here, and that's your phase 1. You want to remove all the debris and get that out of the way. And I will say a couple things there, a couple more points, is that you need the proper velocity on that, to do it, to get everything that's suspended out of the way. And there's a couple ideas you can do. You can do you can segment part of the system. So if you're trying to get, I'm just going to use this for now, 5 feet per second, you may have to segment certain components of the system. We take into consideration, we engineer flush plans for every system. It's custom process to consider the pipe and what do we need to move the velocity through each portion of the system. Sometimes that requires balancing to ensure that you get the flow through all the systems, and then also filtration. And typically we will filtrate at 50 microns, and then we will get it down to 5 microns. And again, the goal is to get the heavier dirt and the debris out of these systems to set you up for the chemical insertion. The next, go ahead.
You got Russ. You want to take it, Russ, as far as this part?
Go ahead.
All right. Yeah. So on phase 2, and that's where, water treatment providers come in, it is the chemical treatment phase. And one way of looking at this is that it's a multi-step process from a water treatment standpoint, where, from Russ's side and on the mechanical, it's more of just all phase 2. But that's really where we're looking to clean, passivate. If it's a large system, we have to sterilize. And so we're putting that chemistries in various types in order to achieve that. Jonathan, I don't know if you want to go to the next one. Yeah, so step 1 in phase 2 is cleaning, right? And this is probably the most important step in bringing any new system online. And the purpose of it is just to remove any oil, grease, dirt, mill scale, corrosion byproducts, other debris that's still kind of clinging to those pipe walls after Russ did the initial freshwater flush on there. And the typical chemistries that we use, HEDP, PCA, surfactants, and it's just all meant to bring all that kind of into solution into the bulk water. So that it can either be filtered out or flushed out at a later time. The circulation time on this is really important. We're looking at 4 to 6 hours, at a minimum, right, of chemical contact circulating through that system. But I mean, and Pat has a great analogy, to where it's kind of like, how long do you wash your clothes for in the washing machine, right? It's like, when do you stop it? You can keep it going, and it's not going to hurt anything. So if you want to do it for 24 hours because that aligns with your timeline, that's perfectly fine. But really 4 to 6 hours minimum, there, and then immediately upon completion of that, you want to then follow that back up with a freshwater flush to then, expel all those kind of particulates and byproducts that are now in the bulk water, out of the system. But yeah, that, going on this one, step 1 of the cleaning is, the most important. The velocities matter, as Russ was saying. If you try to, flush this with a garden hose, not only are you going to be there for weeks on end, but you'll probably end up doing more damage in the long run. So really just following those steps and having a good plan in place beforehand.
Hey, Paul, let me chime in one other point. So when you're flushing the particulates and the heavy debris, that's at a higher velocity. And I believe I'm correct in saying this, y'all prefer a slower velocity when you're circulating the chemistry, the clean chemicals, and usually it's 3 feet per second or lower. Am I correct on that?
That's correct. Yeah, about 3 feet per second on there just to get that contact time. And if you're thinking of kind of like a brush, we're brushing those pipe walls as it's going through.
Okay.
Yeah, step 2, this is, often overlooked in it. It's really useful and critical on large systems that are then getting tied in. So you have a large chilled water system that might be 3 million gallons, and you're going to add on additional leg that's 1 million gallons per se. And one thing we want to make sure that we do is not contaminate that existing system, which is why this entire process happens and the bypasses. So we're treating these systems as standalone, even though at the end of the day, they're going to be tied in. The one way of doing that is with oxidizing biocides. And there's two preferred methods on that one. You have your chlorine, your sodium hypochlorite, or chlorine dioxide. Both of them, need the same contact time around that 6 to 12 hours. But the one key that needs to, if you take anything out of this, is if you're using sodium hypochlorite, you have to flush the system following that circulation time to get your free chlorine levels and your chlorides down to kind of prevent the system from getting into a corrosive state, with those additives and byproducts. Chlorine dioxide, you don't need to rinse or flush afterwards. You could just move on, to the next stage. But one thing of making note is, especially as an owner, to maintain your warranties and everything, you want to pass that through with those manufacturers just to make sure it doesn't void anything or cause any issues down the line where they can just come back and say, we're not going to warranty this work because you did that, even though it could have been something where the chemistry had nothing to do with it. It's just more of protecting yourself from a liability standpoint there. And like it says, we can use, alternative biocides. You could do non-oxidizing biocides. It's just the cost, would skyrocket based on the ppm feed rates you would need. And that's price per pound used as far as industry standards go there. Yeah, when you get done with all that, so we cleaned it, we flushed it, we sterilized it. Now we're passivating that, right? So this is all good. Now we're going to set that pipe up and we're going to keep it so it's going to stay there, till I'm gone, Russ is gone, Jonathan's gone, Pat's gone, everyone's gone, right? This pipe's going to remain, in this perfect state, very little corrosion, and we're going to get it going. So when you're considering that, right, we have, is it an open loop or closed? Because that'd be, different type. What's the metallurgy? A lot of things now we see, especially on equipment, is the utilization of aluminum. Well, aluminum has very strict requirements that you got to stay within, or you're going to rapidly induce corrosion. pH, other things like that go into that. The consistent flow during startup. How long do we have until there's a load on the system? As Russ mentioned earlier, the discharge permit restrictions. So we might have to switch chemistries based on that. What's the makeup water, right? Is the makeup water of good quality, or do we, need to really look at filtering that or removing something that might cause an issue? This process uses, typically phosphate-based chemistries, but there might be some other options, being that the film-forming amines, but it's a case by case, looking at each individual system, and it's not a blanket program for every site and facility. Yes, this kind of just, going on a little bit more of the different options we kind of talked about. So the standard treatment that you'll see, across the board, especially if it's just a lot of carbon steel, mild steel, copper throughout the system, is just a blend of orthophosphate, polyphosphate, and polymers that go in there, and you're really shooting to get that ortho up above 100 ppm and kind of circulate that for that 3 to 5 feet per second for anywhere from 24 to 48 hours. Following the completion of that, you want to just, start another flush and just try to get all that chemistry out of the system back until we get that ortho below 10 ppm. And that's the critical thing there, is that if you don't have the proper, circulation rates, dump rates, fill rates, if you're trying to do, 48-inch pipe with a garden hose, we're not going to be able to get that out quick enough. So then as you're bringing in that fresh makeup, you're also bringing in oxygen. Oxygen and mild steel do not get along, that well. And that's why if you start to see where this flush is taking more than 24 hours, you got to increase that pH up to kind of help that flash corrosion demand, and then add in additional chemistry to, for that additional protection. And when that's done, you just shoot it with the your final corrosion inhibitor that you guys chose. The alternative chemistries that I talked about, those fill-forming amines, they work great in aluminum systems because they don't have the borates and other, additives that really kind of bring that pH up, right? So, you could feed film-forming amines. It's a neutral pH product. It's around 7.2, 7.5, around there. And so the entire system will stay that way. And after you get that, you don't need to flush like you would with the traditional ones, because we're not trying to get the ortho out of the system. So yeah, like I said, it's great for systems that have that mixed metallurgy, and it's kind of an additional alternate option for you.
All right, you want me to talk about the rinse there, Paul?
Yeah.
Okay.
Go ahead, Russ.
Yep. So back on the rinse side of this, that the phase 3, once you're ready to get your chemistry out, you're fixing to go in with your final chemistry, if you will, the inhibitors that are going to remain. A couple of thoughts on final rinsing. So when we're rinsing out a system, again, and Paul touched on it, it's a good point. Your makeup and your discharge become critical. A lot of times, the faster you can do those things, the better. You're trying to maintain a lot of different things that are going on in the system, and the longer you go, it's just like you said with oxygen and mild steel, iron content. You're trying to get below typically 1 part per million, probably less than that in some cases, and so that's kind of just a typical goal. But anyway, you want to remove the chemicals. So what we do, again, we continue circulating in a closed loop, in a circle. Think of that as continuing to being pumped and filtered, and you're bringing in makeup water, clean makeup water, and you're discharging. So there's a dilution process that's happening. And this is one thing that a lot of people miss. If you had a 100,000 gallon system, it's going to take you at least, in most cases, 500,000 to 600,000 gallons to rinse it. And so we deal with systems that take millions of gallons, and it's kind of, we start thinking about the size of it and the volume of how much water we're going through. It's like, it's unreal. But a lot of times we've seen sometimes even 8 times the volume. So just keep that in mind. You need a thought in when you're rinsing. And again, that's why really contemplating, where's my makeup water coming from? How much can I get? And can the discharge equally handle that amount? One point on that, this was there are other things you can do, and this picture here is from a high-rise medical building in the Texas Medical Center in Houston, Texas. It was an add-on for Memorial Hermann. It was about $1 billion build, and this was the parking garage below the campus. And they are one of the clients of TECO, a great IDEA member, and Thermal Energy Corporation, and they serve this building. And so we had to meet the criterias and to move water fast enough. You sometimes have to get into creative solutions. This one involved 14 frac tanks that we created. 10 of them was a water battery, 21,000 gallons apiece, and connected those together and was able to meet the requirements to rinse it within a certain parameter, certain time frames, and get enough water through it, and then have a place to store it, because believe it or not, the pressure is very low in that area. The makeup water was very limited, even the Texas Medical Center, and then the discharge was quite limited. So we didn't have what we needed, so we had to come up with a creative solution. And this can be done for other campus environments and other scenarios. Just something to think about.
All right, yeah. So then after that final rinse, we're looking at, what are we going to do with that system from a chemical standpoint, right? If you're not going to be put online within 2 weeks, you need to lay that system up in order for protection. If not, Russ will be back out there again, and the chemical bride will be back out there again, repeating those steps to get that system back online, ready to go. Do not leave it for more than 2 days just sitting stagnant, without any treatment in there. Once again, it's just, allowing for the possibility of corrosion to start. If you're going to put that system on in the next 2 weeks, you can put your final corrosion inhibitor in there. Like to still keep that circulating for the necessary time to get good dispersion of that chemistry. So it's not just a slug dose going around the system. We, kind of allow it to do what it's designed to do. And the main thing, after this is no system should sit stagnant for more than 3 days without circulating time there. Because if you just leave it, it just opens up, the cases for all those bio issues, corrosion issues that can attack the pipe. So we look there. So now we're going to kind of get into somewhat of those. The layup procedure would be a pretty standard layup procedure. Would be a sodium nitrite molybdenate based product, where where you're really kind of juicing that system up with enough, inhibitors, that are well above the normal operating parameters as a ppm. But the system needs it, right? We want to limit the amount of any potential oxygen entering the system. We want to protect that pipe from biological induced corrosion. We get there. So when you wanted to do that, we want to make sure that we, like I said, circulate it through the system, get a good dispersion of that chemical through there. This can be laid up for an extended period of time if you wanted to, but maintaining the circulation at least every 3 days for 8 hours. That's a must. And then from the chemical provider standpoint, while it's laid up, it's grabbing, testing the system every 30 days to make sure that the residuals are still consistent and we're not seeing a change or a drop, or, it could be a leak, or somebody's going to, unfortunately fill up their water cooler for the day and they see a hose bib and, they don't know it's coming off of the pipe. And also, at this time, you want to review your discharge permits and limitations from the city to make sure that, when you're ready to bring the system online, that this won't cause any kind of issues. And like it says there on the end there, another big one is just making sure that this is done within 48 hours of that final flush. If you're going to lay it up, there's other options. If you wanted to nitrogen blanket, if that's easier, you could do that and just, monitor those levels. If it's going to be multiple years before it's brought back up there. But that's kind of, once again, if it's a case-by-case basis and designed specifically for your site, your system. But, a nitrite or molybdate-based layup is the most common. All right, so we did all that. You decided, hey, I'm going to get this up within 2 weeks. What treatment am I going to use, right? So you have 3 basic, common treatment strategies throughout water treatment. You have your nitrite, azole-based one, which does really well, especially in closed heating hot water loops with the temperature. It stands up a little bit better to that. Not suitable if there's any aluminum, that's present, and that's because of the bore rates we talked about earlier, those pH limitations that it has. So you're really on the chill water, you're looking for that 800 ppm, sodium nitrite, a little bit higher for all the added protection on the heating hot water side. Once again, about every 30 days, on these size systems, you really want to have some on-site analytical field tests ran, just to make sure that residuals are still holding strong. One downside to a nitrite, based chemical program is that as nitrite breaks down into grades, it forms nitrates, not nitrites, nitrates, which actually, become bug food. So it promotes microbiological growth in a sense, as the natural degradation of the product happens. So that's one thing just to keep in track of. And there's ways when you're testing, if your conductivity remains consistent, but you're, losing nitrite ppm, well, then it's being consumed by microbiological growth. Where if you have conductivity drop and nitrite levels drop, then you're losing water. So that's one easy way of kind of telling. But you could also do microbiological analysis. Anaerobes, aerobic bacteria, IRB, SRB, on your system to make sure that it's fully sterilized and you're not having any kind of issues. The other one would be a molybdate azole. And you see that there's kind of a common theme with the triazole added. That's your yellow metal protection, your copper, brass, bronze. Most of your evaporator tubes are, rifled copper. So, that's really what we're looking through there. And that's why you see that common theme across there. So even though the first, molecule changes, there's always that TTA in there. On the molybdate side, we're looking about 75 ppm on the chilled water, 150 ppm, there for the hot water. And so once you want to circulate that through the system, keep that going. You could lay that up again with that if you wanted to. So if your final corrosion inhibitor treatment is a molybdate triazole, you could lay it up and then bring it back up online. You don't have as many problems with the biogrowth as you do with nitrite. With the molybdate option, and then bring it up to the final one, and the pH is still a little bit wrong on that slide. You actually don't get enough or as much pH increase with that one, so I do apologize there. But it would still be within that same 8.5 to 11 range is what we're looking for. But with the silica azole blend product, just 20 to 40 ppm as sodium silicate, and that's above what makeup quality is. So if you have 10 ppm coming in with your domestic makeup water, then we want to be 30 to 50. So it's not just, oh, I'm at 20, but you have 18 ppm coming in from the city. Well, then you really only have 2 as far as chemistry. And above that above 10 ppm azole, that's kind of an industry standard. Looking there, that's a lot of protection for those yellow metals. The nice thing, especially in a large TES system, silica is a little bit more cost effective, right? It works, better if you have a slow leak in a system or, sporadic water loss. You don't kind of lose all your chemistry and protection at once like you do with the nitrate and molybdate based products. So it's great for, any systems that are open to atmosphere. And it's very resistant to biogrowth, contributions. And it's kind of hardy in that sense. So in the university, higher education market, district energy, any large closed loop system, we tend to see, silica azole as the primary choice of chemistry.
Hey, Paul,
Yes.
let me kick this one off here. So I love this slide because the best way to avoid the need for remediation is to commission a system properly. So that's a great statement, but the reality of it is there's many people operating decade-old systems. They're adding new buildings to old systems. Their system has got away from them. We've seen situations where district plant could not shut down, would not shut down, but had a super high iron content of say 8 parts per million, and they kind of want to reset their system. And in that particular case, they actually had a sand filter in place. Some of them will have air dirt separators, but the system literally gets away from them for whatever reason, not chemically maintaining it over the years, adding a bunch of new things that get shoved into the system or what have you. So there are opportunities to remediate, and what we do on our end, working with ChemAqua and such, is that there's some analysis that you can do, and I'm gonna actually let you talk a little bit about that. The physical side of it, let me talk about that, Paul, and then you can talk about the chemistry side. Is we can go in with these large filter vessels and try to, in a very timely manner, filter particulates and clean the system back up, try to get it back to a point where you can maintain it and improve your maintenance and efficiency, et cetera. So we're seeing more and more of these and being asked these types of questions, and that can be done on a delta pressure scenario with filtration at some point, sometimes, and then sometimes we'd actually have a pump pulling out of your system, circulating it and putting it back in. So that option is available, and it's typically can be done while your system is online. It's not ideal, but it's something that can be done. Paul, maybe speak a little bit to the chemistry side of that.
Yeah, most definitely. And that is a great point, Russ. So, if you have 8 to 10 ppm of iron in there, and, from an analytical standpoint, we do a particle study analysis, a PSA, and we find out that a majority of, your particulates in the system on the iron side fall within the 1 to 2, micron size frame. But Russ is like, hey, I got a 5 micron filter out there. So, really we wouldn't be doing much good in that sense as far as removing it, right? You would be removing a lot of other particulates that might be in that system, but that main goal of getting that iron down wouldn't be achieved by hitting that. So we can use some chemistries that can get added, coagulants, HEDP, to kind of sequester that iron, pull it together, drop it out, make it bigger, so then rust could get it out the system. So it's really working together and understanding that, filtration is a great way, but if you can't actually filter it, then, you're kind of wasting your time. So from a chemistry standpoint, we can help Russ, in a sense, clean that system up quicker by getting the molecules at the right size that it needs to be in those particulates in order to get filtered out.
Yeah, I think this thing here, what we want to talk a little bit about is on your new system. Just a couple of considerations is, really from an engineering design standpoint, make sure you don't undersize the pumps, and you got to have velocity to move systems. And this goes into people turning systems off at parts of the year and different things like that. These are things that all need to be considered when you're trying to maintain the system. And you kind of go back to how we talked about commissioning a system and you're laying up a system. You may want to think about what you're doing in your procedures and processes in your campus or the system that you're maintaining, because that can cause a problem. And you can have permanent side stream filtration and or air dirt removers installed as well. But I think those are good. But the thing that I've observed just as a person on kind of the other side of the fence is really your chemistry treatment program is just, it's so paramount, because I've seen where I know people that have different campuses and things they've maintained for several decades and just have no issues. Things are really clean. They've really done a stellar job of maintaining the chemistry and such. And then we've seen a lot of others where that is a problem. And then, of course, not flushing and cleaning new buildings that are being attached to a larger system can create a big problem, because you'll insert those contaminants.
Yeah, Russ, if I go a little bit on that one,
Sure.
Give yourself realistic timelines, right? I mean, sometimes we'll be like, as a water treatment, provider, I'll get a call and it's like, Thursday, and they're like, hey, Monday, we're starting this. And it's like, well, I'm sure the building just didn't get completed in a day, So having those timelines to get those plans in place, so it's not just thrown together, because that's where a lot of times we see where the shortcuts get taken, right? Because they, mechanical contractors and engineering firms have that deadline, we need this building done by this, or it's going to cost us X amount of money for each day that we go over. But from an owner and a facility standpoint, you really want to make sure that your system is treated, passivated, clean, up to snuff before it even comes on there. So that's kind of, if you give yourself that time, and reach out to the appropriate vendors, beforehand, that way things can get staged. If it's a design issue or something, like I know this one here with the dead legs. Dead legs are a huge issue with microbiological growth and corrosion, and just contaminating the system, just because it slowly leaches out bacteria and organisms. So really, you could hit that as hard as you want with biocide, but you're really only going to kill the outer layer. You're not really going to be able to penetrate deep enough down into an area that doesn't have any flow. So from a water treatment end, now I know the picture on the left, that's going to get buried. You don't want that out there. But the only way we could possibly do that would be on the end of each one if they had a tap and we injected chemical from the back end. But that's buried, so without having a proper bypass, and if you're at that point in the process and design, any kind of changes are going to result in delays, right? So can you put a bypass in there at that point? You're probably going to get a lot of pushback, and that might even be written up, in your final, documentation from a water treatment company that is, kind of putting everything out. This was our quality during our flush. This was our passivation period. So you have those final owner documents. There might be a comment in there that says, you had 4-foot pipe dead leg, for 18 feet. And, that could result in that. So if you're looking there, just by giving yourself that time and bringing the people in, it allows you to find these issues and minimize liability down the line. Because those bypasses, they're very easy to put in, and they're a game changer. But more importantly, just limit the dead leg size. I understand the need for expansion and planning, to go ahead. But, if you can minimize that dead leg to the smallest length possible, well, then you're not going to have those same issues.
Yeah, you're spot on with that. And this touch a little bit more of that when you're flushing it. Just think logically, if you've got a long dead leg or future pipe and you're just running debris down a channel, it spins off into that and you can't get out of it. So it is good to think about having some connectivity points in there. If you can circulate your chemistry, that's perfect. If not, keep it very, very short, no more than 2 times the diameter has been kind of experimentally proven to be the worst case scenario. And then also you may want to add blowdowns or things like that during the flushing process. So those areas can be cleaned, because rare mechanical systems are perfectly designed and you can do every little thing you want. But these are just hopefully some pointers that will help everyone as you're planning your next new build, you're working with your architect, engineering firm, your MEP. These, you're trying to figure out what went wrong before. These are real good real world things that we've encountered that make a world of difference. And sometimes a little bit more spin on the front end can save you a lot of headaches.
Yeah, and regardless of size, treat every system as a standalone. Even if it's going to get tight, just say, oh, well, it's a 100,000 gallon loop going into a 4 million gallon. It's not going to do much damage. Well, it can over time. So just treat everyone to be a standalone, and then when it ties in, you're covered on your end. Yeah, it's just kind of a little, get clean, keep clean, right? So once you get that system, clean, passivated, keep it that way with the proper chemistry, filtration, expertise testing, any kind of equipment and oversight, that way it kind of, allows for that added protection and asset. It's a lot of money to put these systems in, from cost of installation, cost of materials, so we want to make sure that ends up stays in, protected for you guys.
Well, Russell and Paul and Jonathan, thank you very much for that. Their information actually is up on the screen. As we speak, it is worth noting that both ChemAqua and PurgeRite will be exhibitors at the Campus Energy 2024 conference. Registration for that conference is now open. What I wanted to do is we have received some very good questions that I wanted to allow the presenters to answer. First thing I wanted to start off with is before we get to the more technical questions, there was I want to call it a business question that was posed. In fact, I'm going to try to combine 2 questions. One question is, and this is pretty big picture, and whoever would like can answer that, is what does either PurgeRite or ChemAqua need, specifically probably PurgeRite, what do you need to provide a proposal for flushing a new system? And as a follow-up question to that, is PurgeRite typically retained by the mechanical contractor or by the owner?
Yeah, that's a great question. Typically, we are a subcontractor to the mechanical. It's usually the mechanical's job to install a new system and to assure that it's hydrostatically tested and cleaned for commissioning. The other part of that, when we put a proposal together, the key things that we look for are what are the specifications that are typically the mechanical division 23. There'll be usually a couple components in there. One may actually get down into the details of what the engineer has specified for flushing velocities and durations. And there's also a chemical treatment section typically in division 23. Sometimes they're combined, sometimes they're not. And it will speak to the chemistry side of it. A lot of things Paul touched on, like they want it circulated for a minimum of 48 hours, or it may say we want it flushed at 10 feet per second for so much duration. So we look at that, and then we look at the mechanical drawings. We look at where would we connect our equipment, how would we connect our equipment, and then go back into all those calculations for flow to maintain a certain velocity throughout the system. What bypasses do we need, valves, etc. And we do look at it based on how the system is designed. So the optimum place to connect in is sometimes to despool the pumps, because that's how the engineer designed the flow to work. And if that doesn't work, we'll sometimes go, there's other options there. We have to look at the whole design, but that's typically how we look at it. So really it's getting those specifications, getting the drawings that allows us to put together our proposal. And our proposal is essentially based on equipment and time. It's not real complicated, and it's usually a flat rate price to the mechanical, so they know what the cost is going to be.
Terrific. Thank you for that. Few questions. These are going to be more on the technical side, and I'm going to try to combine some questions since some are along the, at least as far as certain topics, multiple questions about a similar topic. So I'm going to try to combine them in the interest of time. In terms of the initial flushing, what is the minimum velocity of water flow that you would like to see? And as an adjunct to that question, another question was, what is considered high velocity for chilled water system piping?
Yeah, so the thing that we like to see typically is 5 to 7 feet per second velocity to remove debris, and then we like to tune that down to 3 feet per second throughout, or maybe a little bit less when we're circulating soaps or passivators or etc. We have seen everything to the point of 12 feet per second and down to no requirement. So we have found the best industry practice that we can find out there has been that 5 to 7 feet per second. And we've done some testing, and we're in the process over the next year and a half of doing some more data points and testing along those lines to validate some of these velocities. So that's basically how we look at it. We feel like we can remove most debris doing that. Now, the one complexity I will say, if you start putting in 48-inch pipe or bigger, and you want to do 5 feet per second, it is some of it crosses the line of where is it practical and what do we really need to do that. So those sometimes get wrenched down a little bit in velocities that they require, because the expense and the cost of doing something that large enters into the equations. But did that answer the question, Scott, you think?
Yeah, I certainly think it did. And I do want to remind everyone that for any questions that we don't get to, in case anyone has to drop off at 2 o'clock, and we're going to go right up and probably until 2:15 with these questions. These questions will be sent to the presenters. So even if there are follow-up questions or we don't get to any questions, stand by for your answers in the coming days. Had a question here about that I thought was good and I wanted to pose to you. For chiller plants with year-round operation, what is the best practice for open loops on standby for extended operational readiness? And I think
on that one there, and probably from a water treatment standpoint, would be that if you just think of it in a sense as every drop of water sees every biocide feed, right? So if you have standby systems or offline chillers, if you feed an oxides and biocide Monday, Wednesday, Friday, with a Tuesday for your non-ox, or whatever your schedule might be, just have those offline systems. They don't need to be turned on and run with load. We just open up those valves and allow that water to go through it, so they're not sitting stagnant. So you're moving that water around, you're getting that biocide whole time and treatment in there, and then it would just shut back up. So it's working with your water treatment provider, reviewing that schedule, and then usually it's just a program setting, within your mechanical side in order to achieve that, that synergy. But yeah, if you don't want to have systems sitting offline for too long.
Yeah, and this is Pat Guccione. If I can sort of add on to what Paul was saying, for systems that are run intermittently like that or have to sit stagnant, it's always good to consider a prophylactic mega dose of chlorine dioxide maybe once or twice a year, or depending on your system, maybe even quarterly. It's getting to be very common practice to do that, especially if you're going to lay the system up for 30, 40 days and then bring it back online. You may want to hit it with an extra large shot of something like chlorine dioxide before you bring it back online.
Thanks, Pat. The next question, which I'm going to combine two different questions from different attendees because they both concern makeup water. The first question came in, and I think this was in the section when you were talking about makeup water, is why is makeup water important in a closed loop flush? And the second question about makeup water is, why is there a need for the large amount of the makeup water?
Okay. Well, the makeup water, first of all, let me get to the back end of it first. The 6 times that we talked about the large volume. So when you're diluting, you'll see some specifications that will say, fill up your pipe, circulate it with the chemistry, and drain it. And when you do that, you introduce flash rust. So we're not a proponent and never have liked that procedure that has been out in the universe for many years. And we have found it to be much more effective and much better for the systems to actually bring in makeup water and discharge makeup water, all while circulating to dilute the chemistry down, get it back to the makeup water quality, insert your inhibitors before you and circulate those before you seal it up. So that's really the key thing there. Now, when you're circulating, and I call them the soaps, but when you're and ChemAqua will have their nomenclature. But when you're doing the cleaners and those types of things, you're and y'all can correct me if I'm wrong on this technically, but basically you're pulling iron off that, you're stripping iron off the metal, and you'll see the iron start climbing. And when you're trying to manage that iron, you're trying to get this done as quick as possible. You can bring in makeup water and discharge that too to get your parts per million down to where you need it to be, which is typically less than 1. And some people want it a lot less than that. So that's where the water comes into play. It's very important. The more water you have, let me put it this way, the more water you have, the faster you can do certain parts of the procedures. And the faster you can do it, we've always seen that be a plus. It's better for the system overall. Paul or Pat, y'all may want to add to that.
So it's kind of, one, if you're looking at the quality of your makeup is, if it says that we need to get iron, for on our final flush down to 0.5 ppm, and maybe, your domestic water coming in has 0.25 ppm iron coming in the makeup just because the old pipe from, the city or something going on there. Well, then you need to know that right away because you'll never really be able to get that flushed all the way down to that low point, right? So you're trying to chase that in, but you have so much coming in with the city water. The other side is what Russ was saying is that you're not doing a complete system turnover one time, right? It's if you think of it kind of like a pool, you might have a 100,000 gallon pool, but you're only filtering 20% of that at a time.
Right.
So it's very similar to that. So when you're doing those continuous bleeding feeds, you're not turning that system over at a 1-to-1 rate. And that's kind of where I think some of that, where it is a lot of water usage, but it comes in there because it takes that much, like on a pool, you're looking for, 10 to 13 turnovers for that entire body of pool to see filtration.
Great point. I forgot that point. Yeah, when you're trying to dilute something out of that, you're not pulling 100%. You're only getting a little piece of it every turnaround. So that's why it takes some time to do that. But appreciate that, Paul. Good point.
Another good question came in that I'm going to try to combine two questions here. Can you say a few things about the considerations for flushing and purging large systems that are 2-pipe systems versus 1-pipe systems connecting buildings?
If I understand the question, really all we care about is a circuit. Let me put it that way. It's a closed loop circuit. And if the chemistry is the same, we can combine different types of pipes. So for example, we have been asked to flush, let's say a condenser water pipe was just one direction, and there's chilled water pipe. We can bump off those to another one. We've done heating water and chilled water piping at the same time by connecting them together. But that kind of depends on, is the chemistry allowed to be the same in both of those? And with ChemAqua, I know in cases we've done some of those, so I know they have that. But so as long as we can get a circuit, it's not just a 1 mile piece of pipe going from building A to building B. It can be flushed hydronically. So that kind of would be my comment, and hopefully I'm understanding the question correctly.
I think so. Question about the actual piping itself. I'm going to combine a couple questions here. Is what PurgeRite does, or what you've been discussing, is it only for steel pipe, or would it work also on HDPE pipe? What if the pipe has a liner installed? And then someone else asked,
Yeah. That's a good question. Yeah, I should have answered that earlier. So, and I'm gonna let ChemAqua, maybe I could speak to what y'all did in Princeton as an example, but they had a large geothermal system. As most people know, all geothermal systems are 100% HDPE going into the cup. Typically, sometimes they'll switch over at that point to carbon steel. You also are seeing a lot of chilled water underground pipe and other piping that will switch over from carbon steel to HDPE. So on the HDPE side, if you're only doing HDPE, we will typically go in and do a clear water flush. So for geothermal systems, you're trying to remove debris, and then you've got to be super sure you get all the air out of the downhole loops, because air can get entrained and entrapped in them, and you can literally lock them up. So you have to remove the air at least 2 feet per second velocity to remove air, and there's a lot of things with the geo side. Now, if you walk away from that, or if it's tied to carbon steel components, that's when you need to introduce the chemistry part, either laying it up or even if circulating it through that volume of water that's going to ultimately go into the steel, because you've got to be able to inhibit that. Poly don't really care, but you've got to have it in the carbon steel. Do you concur with that, Paul?
Yes, that's correct. And I know, Pat, he worked closely on the Princeton project. So, Pat, if you got anything you want to add to that one?
Yeah, and I'm just going to say, from a cleaning and flushing standpoint, materials of construction generally don't make a difference. I mean, you've got to get the pipe clean, debris, right, dirt, mill scale. HEDP doesn't have some of the inherent problems that carbon steel or other ferrous metallurgies have, but there's always enough metal in the system. All right, valves, chillers, condensers, all sorts of things out there, that it's also a good idea under best practice to do a passivation, so that you make sure that you're protecting the metallurgy in the system, even though the passivation isn't going to do a great deal for the HDPE. And just incidentally, we're great fans of using HDPE in any sort of underground piping situation. Mm-hmm. So, yeah.
Good.
Thank you. Question came up on on directions. Do you flush the system in the intended direction of the system's design direction or flow, or do you back flush in the opposite direction of the design flow direction?
Yeah, we flush in the direction that it's flowed. We don't really, on chilled water and heating water systems, we don't reverse the flow. On geothermal systems, you do reverse the flow. So it's typical standard practice that you will flow both directions when flushing a geothermal system, but again, on the chilled and heating water, it's the way that it's designed.
Thanks, Russell. Is there a role for vapor phase corrosion inhibitors?
There is. I mean, especially in the layup, portion of it. Pat, did you want to say something?
Yeah, vapor phase corrosion inhibitor or film forming amine. They're coming into use. They're especially effective where you have a lot of mixed metallurgies. You've got yellow metals, you got aluminum, you've got steel. It's still, although the basic chemistry has been around for a long time, their use as in closed systems or in passivation or in system layup is still fairly new. But yeah, there is absolutely a role for them.
Good to know. We got a question about regulations, and the question was, are some of the ongoing treatment options restricted by local regulations?
Let me jump in on that, because that's really a witch's brew sort of question, right? Especially when they throw in the term local regulations. So, there's probably about 50 or 60,000 local regulatory agencies that impact, the cities and counties around the United States. Some are very open, some are very strict. So yeah, a key step, and Russell covered this on on about slide 3 or 4 where we had our checklist. You have to check with whatever your local authority is. There really is no one answer. A lot of the chemistries that are used to do the cleaning, passivation, and even the ongoing treatment are what we call relatively innocuous. In other words, they're not toxic, they're biodegradable, they're commonly occurring substances. But with that said, there's always some local agency that kind of regulates and doesn't allow anything but water and oxygen, in your system. So you do have to check.
Thanks, Pat. And yes, that is local regulations can mean a lot of things, and there's a lot of them out there. A good technical question came in. How deep in the end use of the hydronic systems do you purge, and are coils or energy transfer stations bypassed?
I wish I could ask some follow-up questions on this, but let's take it in one shot. So essentially what we see, some people require different things, and engineers and some clients have different requirements. There's times where we will flush through the supply and return, the mains, and we will open up the branches at the very end when it's clean to actually run through the coils. And that's kind of probably the most typical thing that we see. There are times where things might get bypassed for a variety of reasons, but in general, you want to do all the big stuff, and then depending on what you're feeding from air handler units or other type of units, the best practice tends to be, once you get the mains cleaned and most of the branch lines, any large branch lines, if there's bypasses down those, you get that ready to go. And then one of your last steps is to open that up. Now, this depends on what is required, because I'm thinking in my mind right now of going from carbon steel to copper and other metallurgy. So that sometimes is worked as a team with the chemical treatment company, what they want, what the customer expects. And then we kind of follow that. We'll write the plan to flush it accordingly. So that, I hope that makes sense. So it just depends on each situation, but if it's got water running through the system, ultimately you can flush down. It just depends on how you do it in the sequence of events.
Yeah, and from a chemical provider standpoint, air handler units, coils, things like that, we would love to see that get cleaned and passivated. And that goes back to that earlier topic of okaying it with the manufacturers, the equipment manufacturers, right? Saying that it's okay to do this flushing. Right. And a lot of times we submit the chemistries to them, which then they see don't really pose any harm, to the mechanical issue, so it won't void their warranties. But it's just going through that process and giving yourself enough time. Because, we would love to see that all go through, because if not, then you're looking at looping each individual air handler. So if not, you'd have a dead leg, so that would go and put in temporary pipe in, then having to disconnect that, reconnect. And we would love that. But it's ultimately checking with the manufacturers of the equipment and getting the A-OK for it.
Yeah, and we prefer to go through everything, ultimately.
Paul and Pat, I know, you guys are experts in this area. We had one attendee, seems like his closed loop system, or at least the one he's working on, is not as a preventative, measure, but his system is already suffering from biological fouling. And I think he wanted to, just ask, boy, what are some, typical ways of cleaning a system that is suffering from that as we speak?
Okay, let me jump in on that one. And let me say that if you have a fairly large system, several 100,000 gallons up to several million gallons, and you've lost control of your biology, all right, it's very important to try and get it back. One of the things you're going to want to do is that for those purposes, the best biocide you can use is chlorine dioxide. And the reason you want to use chlorine dioxide is it's an oxidizing biocide, but it's not as aggressive toward your ferrous metallurgies as chlorine or hypochlorous acid or one of the other oxidizing biocides. The other thing is chlorine dioxide is present in the system as a gas. And as a gas, it moves through the system by diffusion rather than by circulation. And it's much more likely to reach any holdout pockets. So yeah, you would start, you're going to have to work with your water treatment provider. You're probably going to want to make arrangements to bring in a temporary or portable chlorine dioxide generator and, try and add chlorine dioxide till you get to maybe about 5 ppm in every part of the system. If you are going to be in San Francisco, come see us. Between Russell and I, we'd be glad to talk to you about the process and some of the options that are available to you. You may need to add some specialty surfactants or dispersants, again, depending on the amount and type of biological activity you have in the system. Can be done, not particularly easy, can sometimes be painful from an operational standpoint, but very necessary. But once you get it clean, if you do a good job, it then becomes relatively easy to keep it clean over the long term.
Yeah, then on that one, I'd go a little bit more just, reviewing kind of those design issues. Do you have a lot of chillers that sit stagnant, that when they do come online, add to that bio load? Do you have a lot of dead legs, that are contributing to that? So, even if you do get it clean, it's ultimately finding that root cause. If it was just poor treatment, then it was poor treatment. But if it's a design issue, it's then, kind of just looking at it from that standpoint as well.
Thank you, Paul and Pat. I'm gonna pose one more question, and then we will try to wrap up and put a bow on things, as we're actually even a little past 2:15 right now. And for those of you who submitted questions maybe within the past half an hour or so, again, all these questions are going to be going to our expert panelists. Final question before we wrap up: what treatment do you recommend for a glycol system?
Glycol, you could use nitrite with that one. Molybdate, is a good one as well. It's really on a glycol system is making sure that you're at that minimum threshold, which is around 30%. If it drops below that, then you don't have the freeze protection, but then it also promotes microbiological growth. But I think any chemistry goes well with it. On glycol, and Pat, I don't know if that's the same thought process.
I would agree with you there, Paul. The other thing is to consider is it may be worth the small amount of extra money to buy an already inhibited glycol that comes with a corrosion inhibitor built in. That way there's no compatibility issues. And it's kind of all in the same house. And I will say that our experience with the inhibited glycols is generally very positive.
That is good to know. Thank you. And again, we're coming up on our self-imposed, cap of 2:20 p.m. If I could ask you the next slide, please. And we're going to, first of all, certainly, I want to thank Pat Cuccione and Paul Iocci of ChemAqua, as well as Russell Biras and Jonathan Collins of PurgeRite on a very, very interesting and informative, webinar that they've, just delivered today. This is, today is October 4th. IDEA is actually going to have webinars for the next, I believe 4 weeks going. In fact, I think some of the specifics are available on the next slide. That's a listing of there. But I certainly want to recommend that everybody in the audience take a look at IDEA's upcoming webinars over the next few weeks. They include a few things, including two distinct webinars from our friends at Centrio on both their Denver and their Chicago systems. We have a young professionals group webinar coming up a week from today about difference makers in the industry. It's going to feature a very impressive young woman from our friends at Austin at Austin Energy, and certainly within the past few weeks, you see right now, we've mentioned earlier how ChemAqua and PurgeRite both have are going to be exhibiting at our Campus Energy 2024 conference. That is being held February 20th through the 23rd at the Hilton San Francisco Union Square. Registration is open for that event. We encourage you to register for that event. Take advantage of the early bird pricing right now. That is available. If any of you in the audience work for manufacturers or service providers and are interested in booth space, please contact my colleague Tanya Kozel for that. We'll be releasing the full technical program within probably the next week or two. So a lot of great things are going on here at IDEA, both online and in person. So I want to certainly thank again the four gentlemen here from ChemAqua and PurgeRite. Obviously want to thank everybody in the audience for joining in, and we hope to see you several times over the next coming weeks as we are fully within webinar season. So thanks again to everyone who joined us, as well as the presenters, and we'll see you next week.
Thank you.
Thank you, everyone.